I have it at least recorded. It looks like this room is not. Maybe I should talk louder. I would have no that the recording is not being exact. That's probably because I talk with a very, very low voice. All right, so for today's attendance question, we're doing a chi-square test to determine if the die is loaded. Were you able to calculate the chi-square? Right, so this is a chi-square test for thinness of fit. So we're saying if the data is not loaded, then they will follow a uniform distribution. The null hypothesis will be the number on the die after you toss the die should be uniformly distributed, and then the alternative hypothesis will be they're not fitting the uniform distribution. So it's goodness of fit test. We determine that we want an alpha to be 5%. We're doing a chi-square test for goodness of fit. The chi-square for 0.05. Were you able to find the chi-square?
Yeah, sorry.
The true freedom is 5 because there are 6 outcomes, so n equals 6.
11.07.
11.07 is how high we have to get to. Okay, now the calculated chi-square would be the expected value is 150 divided by 6, since we got 6 outcomes. Each one is expected to be 25, so the E is 25. And these are all the value for O. We calculate the chi-square by a summation of O minus E squared divided by E. The expected value, they're all 25, so the denominator is all 25. Numerator is going to be each number minus the 25. The 23 minus 25 is 2, 2 squared is 4. And then the 26 minus 25 is 1, squared is 1. And then 23 minus 5 is still square root over 4. And then 21 minus 25 is 4 square is 16. 31 minus 25 is 6. So that's square root equals 36. And 26 minus 25, and that's 1. So altogether, that's the summation of the chi-square. What do we have?
2.48.
So it's 2.48. So it looks like the deviation is reasonable. It's not as high as 11.07. So the result is, we have to answer, we reject the null hypothesis. So we're rejecting the uniform distribution, right? We do not reject. Yes, so the evidence of 2.46 is not high enough than the 11.07, so we do not reject. Therefore, it is uniform distribution, and the die is not loaded. So to answer the question, do the data provide sufficient evidence to say the die is loaded? We would say we do not have sufficient evidence. The answer is negative. That is an example on the test for goodness of fit. Online today. All right, anyway, so that pretty much is today's attendance. I just wanted to use that question as a review for the chi-square test. Our first example of chi-square test will be test for That's for goodness of it. Okay. You said there's no question? Right. So we're gonna continue, try to finish the chi-square test example that we started on Wednesday. In our textbooks, chi-square test covers section 1 and 2. Last Wednesday, I started talking about point 1. Chi-square has 3 different purposes, and we pretty much mentioned the test for goodness of fit. Basically, to determine if the data fits a certain model, you set up your hypothesis, determine your alpha, and together you should also determine the chi-square, the critical value for the chi-square, and then you calculate the chi-square from your actual data, and then you're going to compare whether this chi-square falls into the rejection region of the chi-square curve, or you can calculate a probability, a p-value from this chi-square. Normally it's the right tail to determine if it's bigger than alpha. If it's smaller than alpha, we will reject the hypothesis. And this is something that we had last time, and you can try with the chi-square function in R to do numerical calculation. And this is our second example, just to determine if the data follow a Poisson distribution. And this is one of the examples that you can convert a numerical data into a field category and then turn that into a chi-square test. So that makes the chi-square example possibly to cover even the continuous case. All right, so this is for test of goodness of fit. And then that was the test for goodness of fit example, where you have to present your frequency vector. You also have to provide your probability vector in order to tell if this data, which presented by your frequency, fit this model, which presented by the probability vector. Okay. Now, and let's look at, and that was the example for what I did with the R coding. If you want to determine if the data fits a Poisson distribution, you got to find out the theoretical probability, which is what you present in P1, P2, P3, P4. And then you also have your own observation, which is already in the question statement. Okay, so this is another example. Suppose in a region, the ratio of red, yellow, and white tulip is 3 to 2 to 1. Okay, so if you have, so the percentage will be 3 out of 6 for red, 2 out of 6 for yellow, 1 out of 6 for white. So that will be your vector for probability. And then with the actual settings, suppose you are looking at a bunch of tulip and find out that the red is 81, the red, yellow is 50, and white is 27. I want to see if this fits the model. So again, you will present the tulip is the word tulip now is a vector for the actual observation. Now that was the theoretical probability. If the model was good, you compare them to say if the observation fits the theoretical probability. And this is the outcome after you run the test. I actually copied that from the R coding. They give you a chi-square, and you can see that chi-square is pretty high. They also give you a p-value, and the p-value is really small, so that is significant. So this is saying that the observations do not fit the model. Because you got a really high chi-square value and really small p-value, they indicated they are significantly different from the probability. Any question? So that's how we can calculate chi-square test result using the R coding. Instead of compare the observation and the expected value, we actually are comparing observation with the probability. That's how R runs with it. Except in the calculation of chi-square that we're doing, we have to know the O and E, observed and expected. And let's see. Okay, so this is another example. This is a test for, we're comparing two methods of instruction. 50 students are randomly selected into two groups. So we're comparing for each group. So 50 for group 1, 50 for group 2. So the total number of students, 100. At the end of the instruction, each student is assigned a grade. And grade is qualitative. I mean, you can see this is one of the situations. Grade is qualitative data, but the numerical grade is actually quantitative data. So grades can be represented as qualitative. It can also be represented as quantitative. So now what we want to determine whether the corresponding probability are equal. Okay, so this is one of the situations we're actually looking at whether these two are equal. That sounds like a test for homogeneity, right? We're trying to compare group 1 and group 2 to see if they are the same. And that's why we're actually calculating a total probability or total probability for A, total probability for B, total probability for C. For example, probability for A, you would take A plus 4, all the A divided by the total, so that's 0.112. Same thing for B, C, and D, E, F. So here the probability at the bottom row is calculated for the total probability, including group 1 and 2. So we're calculating the chi-square for all the observation in the question. So in this case, the observation has A, B, C, D, E. There are 5 for group 1, 5 for group 2. Altogether is 10 observations, right? So we have 10 observations, but here you have to calculate the expected one for A, B, C, D, each one. So if you take the 100, which is the total number of students, and divide it into 10 groups. So the expected is 10 for each box, right? So this is 8, so you go A minus 10, and then squared, and then divide by 10. So that's how this is being calculated. Oh, it's not. Oh, so we actually, I thought they were uniform, but they're not. So it looks like we're calculating the probability for A, B, C based on the actual scenario. So we're using the 0.25 multiplied by 100. So the expected for the first box, no, so 50 times the 0.12. Let's see if that sounds like right. That's right? So out of 50, 12% of 50 is 6. Now for the 4, this box, for group 2, the A is 50 times 0.12, that's supposed to be 6 as well, if the distribution for both of them are right. So we actually have to calculate probability, the expected value for A, B, C, D, E using 100, using 50 times each of the probability. So 50 times this times 0.22 times 0.23, those are the expected value for A, B, C. So these are the E. At the bottom line, N times P, the total for each group multiplied by probability for that outcome is how we get the 6, 11, 15, and 12. Any question there? So basically those 10 number are the O, the observation, and bottom here 6, 11, 15, 35, those are the E, and then we calculate the chi-square. So the chi-square summation of the 10 chi-square have a total chi-square of 5.18. And in this case, we are comparing the, how many are we comparing? We're comparing with a chi-square, a critical chi-square. In this case, the alpha is 0.05, the degree of freedom is 5 minus 1, which is 4. Degree of freedom is 4. So the Q is being compared with 9.488, and that looks like the Q is not larger than the 9.488. So we will reject, we'll say group 1 and group 2 actually have the same distribution, they actually are not different from each other. Even though on the front, it looks like they do have different number for each category, but essentially after calculating the chi-square, we realize the difference is not significantly large. And this is what people call test for homogeneity. So essentially, you're trying to determine if the two groups have the same distribution. All right, any question? So since the difference is not significant, we cannot see there's difference between the two methods, even though the two groups are being applied to different instruction, different method of instruction. This example is another example where you're trying to compare two groups of workers have the same qualification for a particular type of job. And here we have their experience. Right, so we have the salary level in thousands of dollars, and then group 1 and group 2. If we're comparing them, we still have to find the total probability. So the total number of people is 90. So you're going to take the 11 divided by 90 is the probability for the first one. Like if you want to find the observed, that you have to take the 60 times the 11 over 90. That's how we get that number. Right, so essentially this is the 90 will cancel. It's actually 60 times 11 divided by 90. So you can calculate the expected value by row total minus column total divided by grand total. This 90 will cancel, right? Essentially, that's how you calculate the observed value. So you're going to take every single outcome, like 6, 11, 16, 14. That's actually 5 times 2 is 10. So we're adding 10 chi-square to get that Q calculated. And then the total chi-square is 4.752. And then you will compare with the degree freedom, and then that's still not significant. Any question? These are example on what if you got a table. So it's not one rule for O, one over E. This is actually a situation where you have actually two rules of O. You have to calculate your own E. This is the E expected value, the E number. You have to calculate that by itself. Any question? So this is the example. Now, when you have to compare two groups, what you have to do is we don't want to calculate the chi-square table E value. If you have 10 chi-square to calculate, then you have 10 expected value to calculate, right? That is on top of that is calculate 10 number and then calculate 10 chi-square and add it all together. So in R, it actually have a faster process to process that. So you have observation for group 1, which is those 5 number in the table, and observation for group 2, that's another 5 number, which is here. And then we're binding them into a table. R bind is binding the row vector into the same table. So you can look at the tab TAB. It's really putting one row on top of another row. Then what you have is really a table. And then you put that table into a chi-square test, and then chi-square that test does the rest. You will start comparing the column and row. Essentially, chi-square itself will receive the table and start comparing row by row or column by column. And so this is the result. You have a chi-square 4.75. I think it's the same number as what you have here. This one. It also gives you the p-value for the chi-square. It also gives you the degree freedom, which is 4. Degree freedom for the chi-square test, since we have column and row, it's really a multiplication of the degree freedom. We don't count the total. 1, 2, 3, 4, 5, which is 5 column. 5 minus 1 is 4. So, and then we have 2 row. The row is 2. Total number rows to 2 minus 1 is 1. So we multiply the degree freedom. Any question? So essentially, you want to determine if they're independent. But before you determine they're not independent, we assume they're independent. If events are independent, we multiply their probability. And for similar reason, we multiply their degree freedom. So the degree freedom for the chi-square is 4. Any chi-square distribution, you have to know the degree freedom in order to apply to a chi-square curve. Right, so having that degree freedom, you know it's a chi-square, and then you can calculate the degree freedom for the 5% level, and you can calculate the p-value using the chi-square number there. And that seems to be a pretty high p-value, so we do not reject. Any question? All right. Here's a warning on whether the chi-square approximation is right, because in the process that we're assuming the underlying normal distribution, but we haven't really guaranteed that. You can see one of the observation is 2. Whenever one of the number of success or n times p is lower than 5, you see that warning. So if all those numbers in the table is higher than 5, we will not say it's warning. When the sample size or number success, number failure gets too small, we have this worry that the central limit theorem may not apply. That's the reason we get the warning sign. All right, this is the coding for the question 5 in the homework, I think. So you have a similar scenario, you have group 1, group 2, and then you will run, that's the same question, I think, the one after that. You have group 1 and group 2, and you will bind those numbers together into a table we call T, and then you can run the chi-square test to finish that. And I think also provided a couple coding for 1, 5, 7, 13. Those are just example. Any question? All right, so the homework for 9.1, 9.2. So this covers, the 9.2 cover test for homogeneity and test for independence. And 9.1 mostly are covering the test for goodness of this. Any question? All right, I think I only focus on the main part. I might have skipped something. As you work through the example, if you see any question or problem, please let me know. And we're at April 22. I feel like the time is pretty pressing, so I may have skipped some steps, but hopefully with the example in this file, you'll be able to finish the homework question. Let me start the ANOVA test. That's 9.3 and 9.4. So we should be able to compare multiple means. That's the sole purpose of ANOVA test. And pull up the file. All right, ANOVA test. ANOVA stands for analysis of variances. So if you actually knew the actual name of the test, that made it a little bit easier to understand. So why do we shorten into ANOVA? I guess it's easier and shorter. Okay, so ANOVA test covers section 9.3 and 9.4. 9.3 covers one-factor ANOVA test. 9.4 covers two-factor ANOVA test. All right, so let's start with the one-factor ANOVA test. The name stands for analysis of variances. It's a statistical method to determine if 2 or more than 2 means are equal to each other. So if you want to compare the means of more than 2 populations, for example, if you want to compare 3 of them, mean 1, mean 2, mean 3, are they exactly the same or are they different? So we're comparing whether they have the same mean. All right, so for example, you might compare several different corn hybrid. You want to know which one makes higher mean, higher average produce. You might want to compare the mean score after 2 or more method of teaching, right? Or if you want to compare the mean mile per gallon from many different types of the cars. So these are situations you are trying to compare more than two. So if you are comparing them 2 by 2, you have three different type of cars. Then you compare A with B, B with C, A with C, right? So you have to compare at least doing 3 different t-tests. But with the ANOVA test, in one setting, you can at least tell if they're different, if there are any difference. If you run the ANOVA and the result says, hey, they're the same, then no more test, right? But if you run ANOVA and saying they're not the same, and you have to probably draw the box plot for your data and determine which one is higher than other, or which one is overly low than the other. Then you might still have to do a 2 by 2, 1-to-1 comparison after the ANOVA if you see any significant difference. But if you don't see any difference, then that'll be the end of the test. All right, so we did compare 2 means before, which is a regular t-test. In section 8.2, we're able to compare the mean between the two numerical data. But if we want to compare more than 2, then it's not just about the mean anymore. You also have to consider the variances. And we also have to consider the variance even when we're doing the t-test, right? T-test a t equal to mean 1, sample mean 1 minus sample mean 2 divided by square root of variance 1 over n1 plus variance 2 over n2, right? So variance has always been a persistent thing to consider when you want to compare the means. Same thing with more than one. If you have multiple means that you need to compare, you also face a situation you have to analyze the variances or relation of the variances. The null hypothesis stating that they are equal to a same value, and the alternative saying that at least one of the mean is different from the other. There may be more than one mean different, but we are saying at least one, right? The opposite of they are equal is not they are. Each one is different. The opposite of all equal is at least one of them is not equal. So that's the logical opposite from the H0. Right, so numerical example, if you search it online, you can see a couple examples. Actually, if you search it now, there are more. So there are more than, there's a lot of different ANOVA test examples online. Let's see, we're gonna try to go through what we are doing theoretically. In ANOVA test, we calculate a test statistic that's called F statistics. If you remember, we did talk about F statistic when we talk about comparison of variances, right? Variance 1 divided by variance 2. If you divide the two variances, that's an F, okay? Essentially, the F statistic is a chi-square divided by another chi-square. Except you have to take your chi-square and divide it by the degree of freedom, right? Numerator is chi-square divided by degree of freedom. Denominator is chi-square divided by degree of freedom. We do the same thing here. So we'll calculate the variance between the group divided by the variance within the group, and that gives you an F statistics. So namely, the F is try to compare the variances between the group compared with the variance within the group. If the variance between the group is large, you will get a bigger F value. If the F is high, that is telling us group 1, group 2, group 3, they're very different, right? It's really highlighted the difference between the groups. But if the variance between the group is small compared to the variance within the group, that means variance between the group and variance within the group, they're pretty much the same, or even smaller than variance between the group within the group, then smaller F value is indicated the difference is really not that high. A bigger variance indicated variability. Now, if the mean 1, mean 2, mean 3, if they have a big variability, that is really caused by the fact they're different, right? They have a huge difference. So here in this calculation of F, there are a couple of things we should know. The letter M is number of groups. Sometimes I use K minus 1 for the variance between the group. And then denominator is n minus k or n minus m. N is total number of data. So group 1, group 2, group 3, you can add it all together, the total number, how many data you have, that's your n. All right, if you have group 1, group 2, group 3, then your n equal to 3. So your number of groups is 3. And so those are some of the things that you have to know before you do the calculation for F. The numerator have SST that stands for sum of square between the treatment. The letter T represents treatment for different groups. SSE is sum of square within the treatment, or you can also call that as sum of square for the error terms, and error from their own, the mean within the group. So that's SST, SSE. All right, now SST is also called, all right, sum of groups among the different treatment among the different groups or among the different classes. So that's this SST. SSE is sum of square within the group, or you sometimes call the error sum of square of the errors. And you see that subtraction there, individual data point minus the mean within the group is the error terms within the group. And this is the total, the X bar with 2 dots is total mean among all groups. And then the X bar I represent the mean within each group. Here, mean for group 1 minus total mean, mean for group 2 minus total mean, mean for group 3 minus total mean. This is multiplying the number of data points within the group. So this is summation of squares for between the groups. Any question? The top one is total sum of squares. If you add ST with SSE, that's your SST total, SS total. So the bottom equation represents the relation between the sum of squares. Any question? All right, obviously we have to know this in order to calculate the F. So you have to know SST, you have to know SSE, and then adding these two together, you have SS total summation square. This is normally the first thing you have to calculate in order to calculate the F. So people often talk about something called ANOVA table, where the first thing is summation of square. This is between the groups or between the treatment, and this is an error term or within the groups. And then here is a total, right? This is the 3 number you have to have calculated. And then you also have to know the degree freedom. This degree freedom is m minus 1 or k minus 1, because m and n sound so similar. So in some of my example, I call that k, so that k and n sounded very different. And this is n minus m or n minus k. Now here it's going to be n minus 1 because this plus this is this. And same thing, this plus this equal to this. SST plus SSE equal to SS total. And here is going to be the mean square. So you're going to have the numerator is SST divided by m minus 1. So you can take the summation of square divided by degree freedom. That's your mean square. This summation of square SSE divided by n minus I and m. That's the mean square. So then once you have the mean square essentially it's kind of like variance calculation, and then you can calculate your F. You take the mean square for the treatment divided by the mean square for within the treatment. That's your F. And then you're gonna have to look at your chi-square curve and possibly calculate a p-value from your F statistics. All right, so that kind of is going with the logic. If you have all the number, all information organized nicely, you would see something like a ANOVA table. Any question? All right, so summation squares, degree freedom, divide the summation square by degree freedom, then you have mean square. Divide the mean square, then you have the F ratio. Any question? All right, so here is an example. Assume that we are comparing 3 x 1, 2, 3, 1, 2, 3, 4. We're comparing the mean of 4 different data point, 4 different mean. So we want to know if mean 1 equal to mean 2 equal to mean 3 equal to mean 4. Okay, so for each one we have 3 examples. And now we're going to add the 3 and divide it by, so we added this, we get that's 30. 30 divided by 3 is 10. So the last column is the mean within the group. But if you add all of them, that's 3 by 4 is 12 number. You take add it all together, divide by 12, you get 11. So the total for all 12 number is 11. The mean for all 12 number is 11. This is the mean, the grand total, the overall mean, the total mean. This is the mean within the group, right? So we're going to calculate, so for example, you're going to calculate the total summation square. You have to take each one of them minus 11, minus 11, minus 11. Then you get 12 of the summation of 12 number, that's the 80. That's the total summation square. All right, and then we can also calculate summation of square within the group. That is every number minus their own mean within the group. 13 minus 10 squared, 8 minus 10 squared, 9 minus 10 squared, plus 15 minus 13, 11 minus 13, and 13 minus 13. They're all square, and that kind of thing. And that's a calculation for SSE. SSE is summation square within the group. We're not subtracting the all mean, and you're just summating the mean within the treatment within the group. That's the SSE. So the SSE can be calculated by subtraction. You can take the 80 minus 50, that's your SST. Or you can actually look at the mean. This mean, you minus this mean, and then square. So 10 minus 11 square, and you want to times 3, because there's 3 of them. And then the 13 minus 11 also square, and then times 3, since we have 3 number in the second group. And then we do the same for all of them. That's the summation of square between the treatments. So you focus on thinking, what if this is all 12, this is all 9, this is all 13, and you compare with that 11 to get summation square. Any question? All right, and then we're gonna, every summation square divided by the degree of freedom. So the SST, which is 30 divided by 3, and then 50, this is summation square in the error term within the group. So the 50 divided by 8, because the degree of freedom is, the total is 12, there, 1, 2, 3, 4. 12 minus 4 treatment, 12 minus 4. That's how you get the 8. So numerator submissions, SAT divided by m minus 1, denominator is SSE divided by n minus m. That's how you get 1.6, and which is pretty small compared to the actual F value for the degree freedom. The F value is the F curve with degree freedom 3 and 8. 3 and 8 is the degree freedom. The alpha is 0.05. You look at the F distribution, you get 4.07. And do the QF of 0.05 and degree of freedom 1 equal to 3, degree of freedom 2 equal to 8. That's how you can calculate the F value from the R-coding. Any question? All right, having an F value so small, which is smaller than critical F, we fail to reject. So we say we fail to reject, so we cannot reject the null hypothesis. The null hypothesis saying they have the same mean. So essentially, the mean of 10, 13, and 9, and 12, they're not too far away from the 11. They're not significantly far away from 11, and therefore we still consider them having the same mean. And there's no more action after that, if you knew they were supposed to be the same. Any question? Right, so we do not have enough evidence to say they are not the same. That should be the right way to say it. because it could be that they are really the same. It could also be that we do not have enough evidence. To get more evidence, to get a stronger reason, you actually need to collect more data, right? Having 3 number already pose a reason for doubting the result. So maybe we should collect at least 10 for each one, make a more stronger evidence if we are persisting with proving the differences. But right now they're saying, hey, your evidence is now not enough to prove anything different. So this is the process of doing those calculations was on with manually. So we need to calculate SSE, SST, and then adding them together is their SSTO. But you can also calculate them one by one. So I did all the calculations that was on this page, which are first you enter your data x1, x2, x3, x4, and then I tie them together, connect them together into a big data X. So the total summation square is each data minus the mean. Right, that means all 4 sample collected into the X, right? X minus mean, mean of X, which gives you the overall total. So the first one is essentially what we did with SSTO, and the second one is the summation square because the error term. So then you have to do x1, x2, x3 individually. So you have x1 minus the mean of x1 square added together. X2 minus mean of x2 square, and then that's summation of square for this data set. And then you have to take the summation of square for that data set, and you do the same for all. And they're not the same, right? Because this x, the x is the same, because this x repeated, so it's piling all 4 data set into this x. But then the mean is different, right? In the calculation for the total summation square, the mean is for the mean for all of them. So this mean for the first data set, this mean for the second one. So they look like the same, but they're not. Any questions? Right. And here I repeated the same thing, mean for x1 minus the total mean square, mean for x2 minus total mean square, and you add it together times 3, because every data has 3 numbers. Times 3. That's T, and you can see the results yourself. And after you get to that point, once we have the summation square, we can repeat the calculation, like 30 divided by SST divided by 3 over the SSE divided by m minus n divided by 8. We'll get 1.6. Right, any question? Right, so that's the example. Having those example in there, we can fill in the number. To see our ANOVA table, the summation square, there are 30, 50, and 80. 80 is the total summation square. Degree freedom, there are 3, 8, and 11. You see the degree freedom in the calculation. And then the rest follows. You have 30 divided by 3 is that number, 10. This is 50 divided by 8, that's, I think we should have a decimal number. These 2 numbers divided is 1.6. With 1.6, putting into the F curve, you see the p-value. And that's saying that it's not significant. Any question? Any question? All right, this is how you can do it with a ANOVA function. In R, the function for ANOVA test is shorter. It's not called ANOVA, it's called AOV. Analysis of variances, which to me it makes more sense because the number of variances is 3 numbers, 3 words. You were supposed to use an initial letter for every word, right? AOV makes more sense. I don't know why people historically named it ANOVA instead of AOV. So anyway, you gotta have the actual data table, and this is illustrating the right way to enter the data because ANOVA essentially is relation between the quantitative data and the qualitative data. So the quantitative data in this case is the value that we're comparing, and then with every quantitative data, you follow by qualitative data. Like the first one is saying 13 is a x1 data, and 8 is a x2. So those x1, x2, x3 that you follow with end up being a 2-column data set. 1 column for the quantitative, 1 column for the qualitative data. And then we use ANOVA to analyze. So once you have the data ready, you put in your data, and I actually put a header to the data so then we can have name One column is being called value, and the other column is called treatment. We're trying to determine what's the relation between value and treatment. We want to know if the treatment causes any difference in the value. So in this case, treatment is an independent variable. The value is a response variable. So the writing of it, kind of like the linear model function, kind of like try to find a relation. But linear model LM in R allows you to find a relation between two quantitative data. The Y is quantitative, the X is quantitative. But in ANOVA, one is quantitative, the other one is qualitative. But of course, you also have to present the data. And then this result, if you only do this, it doesn't show you all the results. So I save it in the RES, which is the initial letter for results. So the result is being presented into a summary. The summary function is being repeated for multiple scenario. Any procedure that have a complex outcome, it's better to save it in the table and then present it with a summary. Right. And those are the outcome after you run this. Any question? So you're gonna see the same ANOVA table that you see, except in R, the degree of freedom is being presented first, and then summation square and the mean square. So we did switch the relation between the column for degree of freedom and the column summation square. Any question? Okay, so this is ANOVA example. So we have a second example in the text, which giving us a comparison between 5 means. And the null hypothesis is all 5 means equal. Alternative, of course, is that at least one of them is not equal. This is the background is we're doing a test for pull-out test to determine the force needed to force that out of the window. And this is the actual data. So we have X1, there are 1, 2, 3, 4, 5, 6, 7 number for X1, 7 number X2, 7 X3, and 7 X4, 7 for X5. So total number data point is 35. 35 number. So N equal to 35. 1, 2, 3, 4, 5, the K equal to 5. Now, that means the degree of freedom in the numerator is 5 minus 1, which is 4. Degree of freedom for the denominator of the X is 35 minus 5 is 30. So 4 and 30. I'm trying to think about the ANOVA table there. Then you will also need to calculate their mean, but here we actually get it, the summation. Because you can use summation to calculate mean, but then to do the reverse is a little bit harder. So here is the summation of the squares. That will probably allows us to do some faster computation. So the last 2 columns is just to assist the calculation. So let's see, let me do the calculation. Number 1 is we now know that's the summation square for all the summation squares. So that's the summation square, the total summation square minus 1 over n of the total. So with the bottom to the lower right 2 number in page, lower right corner of those 2 numbers, we can calculate the summation of square. That was a calculation of the summation square formula that we learned in the basic statistics. Right, with the same thing, we can calculate the total summation square. Essentially, it's summation square term in each row minus 1 over 35 for that summation square. So once we get that number, subtract them, we can have summation of the error term, and then this divided by the 4, this divided by the 30, we have our F, which is really high. Any question? Right. The top part of this page is the ANOVA table. So you have your summation square, and then you have your degree of freedom, and you summation square divided by degree of freedom is the mean square. Once we divide the mean square, we have our F. So that is it's showing a really big difference between them. So we would reject the null hypothesis, saying that this is very strong evidence to say that the mean of the 5 are not the same. So if they're not the same, I think we clicked on the wrong thing. If they're not the same, we have to have the responsibility of figure out which one is different. And then this is a box plot. We did a back-to-back box plot for all 5 set of numbers. You can grab this 7 number, draw a box plot, grab that one, and that one, and that one. We can actually do back-to-back box plots, and now you can see they're different. So it looks like 3, 4, 5 are pretty much the same. And then it looks like 1 and 2 has difference. The difference is not too big. But then between the 3, 4, 5 and 1 and 2, that difference is very significant, right? So I would run another ANOVA just to tell if 3, 4, 5 are equal. If they're not equal, then we'll look at the difference. I think they're not. They're pretty much just the same. 3, 4, 5, they look different, but the difference is not very big. But then 1 and 2 is significantly different from 3, 4, 5. So a box plot can give you a lot of visual instinct about whether we go further, right? So this is I was trying to construct the table, right? And then now the visual table having the 2 columns, and then enter the data into the data set. So now once you have your data set, you can then try to determine between I put the header on the data, between the value and the treatment, what was the difference, and run that, you get the same ANOVA that you see. You see the F value is 44.2. All the other numbers are the same as what we calculated. Any question? Right, so part of the effort is trying to construct the table. So it's actually, you can see the data table that will be received by the AOV function. It is not exactly the same as you see over there. So we kind of have to spend a little bit of time to work out the table so that the data is in the right format in that function. All right, one of the things is draw the back-to-back box plot. So I did a little example on how to draw the data. The 7 number, x1, x2, x3, I put it into vector. And then I'm calling it name treatment. I'm using x1, x2, x3 is identified as a treatment. So I would draw the box plot, and then the names for every data set is being the treatment. And you can draw a horizontal box plot just to compare them. The name is the title of the plot. Then the label for the x-axis is ponds. And then it will show you the plot. I think I had that. Now, this should present the same thing as it did here. Just want to give you an example on how to get a box plot running, because I feel like a back-to-back box plot is really useful. If things are different, how do you really visually see the difference? And then also have here, if you have the treatment words, you can repeat the words 7 times. So you repeat x1 7 times, and you repeat x2 7 times, and you repeat x3 7 times. And that's what I'm calling n. I started calculating, so I did TR, which is repeating the treatment, treatment, which is this vector, that vector following the format in n, right? And that is that column. So I'm trying to construct this without actually visually do this. At first I visually did this, and this is really time consuming. So this is using R to quickly get that data. There's this function called data frame, which is connecting the column. So I have one column, which is all the x value, which is at x. X is really connecting x1, x2, x3. That's the x in here. Now the group, which is the second column, I'm calling it group. So the group becoming the vector name for that column, and then the column values all those x. It's going to be x1 repeated 7 times, and then x2 repeated 7 times. That's how it is. So that one, I give you the data. Now the data, this is printing the data on the computer, so you can see if they are working as expected. And then you can put in the ANOVA function and run the rest. Just give an example on if you are looking at data, you don't want to manually have them layout in the column, the two column. How do you do it? This is just using another function, the data frame function to set it up. Any question? Right. As far as enter data into R, read.table or data.frame are two of the popular ways to enter data manually. And of course, on top of that, you can read data from a file. That would be even faster. But this is the two that you can quickly enter data. So those are the homework questions for 9.3. Any question? Essentially, 9.3 deal with one factor ANOVA analysis. Why is it called one factor? You see this. You have one column that's quantitative, and the other column, the second column, is a factor. So you can see the quantitative data are being differentiated because some of the quantitative data from X1, some of the quantitative data for X2, some of the quantitative data have X3. And so there are basically four factors. One factor that has four values, right? But what if you have this column, you have another column that's A, B, C. So if you have a second column that is a second qualitative column. So one quantitative, one qualitative, another qualitative column, that will be called a two-factor ANOVA test. So that is when you try to determine, this is to determine whether the X value is affecting the quantitative value. And maybe you have ABC, maybe A, B, C have different value in the quantitative set. So if you have two different factors that affected, you have two different qualitative factors that is affecting your quantitative value, that to determine the differences is being called a two-way ANOVA. Any questions? So what we are talking about in 9.3 is one-way ANOVA. Now 9.4 is two-way ANOVA, two-way analysis ANOVA. It's really to determine the relation between one quantitative variable and two qualitative variables. So visually, you're looking at three different columns. One is quantitative, two of them is qualitative. So essentially, we're trying to look at a couple of different hypotheses. Since we're looking at two different factors, so the HA is a hypothesis saying that depending on different value of the A factor, we have the same. That's called alpha 1 equal to alpha 2 equal to alpha A, assuming that A is number of value for factor A. Now HB is the second qualitative variable, we're calling it B. So beta 1, beta 2, and beta B are the mean caused by a different value of the B factor. Right, so assuming that also have, they all have the same mean, therefore they have the same value of 0. Right, so these are looking at, I think they are representing the effect, the difference that the qualitative variable is causing. So that's why the null hypothesis saying they all equal to 0, meaning that each of this factor has no significant impact in the underlying quantitative variable. Right, then the alternate hypothesis will be at least one of the equality in this hypothesis is false. So at least one of them has a positive impact or has a non-zero impact. Any question? So we're kind of writing it in terms of 0 instead of setting it equal and have a value. So they're all equal to 0. So in here, the beta 1, beta 2, and beta B representing the effect. So this is the ANOVA table for the two-way ANOVA. You can see there's one more rule. SSA is representing summation of square based on the value of A, based on factor A, and SB is summation of square based on factor B, and then the error term is summation of square within the group. Okay, the degree of freedom, suppose A has a value, a different value in the qualitative variable. A minus 1 will be the degree of freedom. Same thing for B. If B has lowercase b represent number of possible value for that qualitative variable. E minus 1 will be the degree freedom. For the error term, you will multiply the degree freedom and that's the degree freedom percent. Denominator. Okay, and then the bottom one is the total degree freedom, which equal to this plus this plus this. It's really the summation. Kind of like over here, the total summation squared is summation of all three. And then the mean square is summation of the square divided by degree freedom for every rule. All right, and this is the F value. We actually have two different F value because you're going to take this divided by this to get that. So mean square A divided by mean square E, and then mean square B divided by mean square E. You have two different F values. Depending on those two F values, you can determine is A have a significant impact or is it B have significant impact. They're not simultaneously. Sometimes A has significant impact, B does not. Sometimes B has significant impact and A has not. That's why we have to have two separate F because we're running two separate hypothesis tests. Any question? Okay. So let's look at a numerical example. So here we have an example. Each of three cars is driven with each of 4 different brands of gasoline. So we have 3 different cars and 4 different gasoline. Right, so you obviously have to do a lot of running with the cars. Car number 1 with gasoline 1, 2, 3, 4. Those are the miles per gallon for each car. Okay, you can see some gasoline lasts longer. You can run more miles with it. Some are less. Okay, and then we do the same for all 3 cars. In this case, we find out their column mean. We also find out their row mean, but the actual data is over here. We have 3 times 4, 12 number. That's the observed miles per gallon. Any question? So miles per gallon will be the raw data. Here we have to determine the degree freedom. You have, if we call A would be different cars, right? Degree freedom will be the number of cars is 3, so degree freedom is 3 minus 1 is 2. Now number of gasoline, there's 4 different gasoline, so 4 minus 1 degree freedom will be 3. Depend on the factor. So there are 2 factors. Does the car causes us to have different mileage, the type of car, or does the type of gasoline cause us to have different mileage, right? Theoretically speaking, the type of car or the type of gasoline should both have some kind of impact. And we just want to say if which one have a significant inferences. All right, so first we're going to test the beta value. Beta will be the type of gasoline. We want to see if the gasoline is causing any difference. So, and then I guess the beta 1 is the difference caused by the first gasoline, second, third, and fourth. So we're assuming on average the impact is 0, but we're going to see if that's significant. So here are the ANOVA table. All right, so we're trying to focus on B here. As far as B, which is the type of gasoline, the degree freedom is 4 minus 1, which is 3. So you can see the calculation here. The degree freedom is 4 minus 1. The total degree freedom in the denominator degree freedom is 3 minus 1 times 4 minus 1, which is 6. Any question? All right, so for the SSB, we want to calculate the degree freedom caused by different. So you're going to take the B, this minus the total mean, and square and times 3. This minus that mean, and then square and then times 3. So we're really looking at thinking this being representing the value of each gasoline. We want to see if the gasoline causes any major differences. So you can see that calculation, it's SSB, and we got a 30. Now, SSE is harder to calculate. because we're going to calculate the error term. You have to take the individual data point minus the column mean minus the row mean and plus the total mean to get summation squared. And then you have to do this for all 12. So this is really summation squared there. So the SSE is a little bit harder to calculate since we have individual data minus this, plus this, and the 28 minus 26, minus 29, and plus 27. And we have to do it for all 12 of them. Summation squared. And that is giving us a 4. Okay, so 4 divided by 6 and 30 divided by 3. So we have 15. The degree of freedom for the F statistics is that is 3, that is 6. So degree of freedom is 3 and 6. The alpha is 0.01. We get 9.78. The calculated F is 15 after the division. 15 is higher than 9.78. This is caused by the fact that the SSB has a larger value than expected. So we will reject the null hypothesis. We will see the B is making an impact. Any question? So we'll say the factor B, which is the type of gasoline, is significant. All right. So all these calculations in this page is on the B. So we have 30 over 4. We have 30 over 3. 4 over 6, and then we divide the 2 to get 15. The A effect is not calculated, but I think you can follow similar procedure. For example, the summation of 24 is calculated by, you will take the row effect, 29 minus 27, and you square, and then 26 minus 27 square, 26 minus 27 square, and then you have to times 3 for that. And then that's how we get the summation square of 24. Okay, give 24. Any question? So this is a row effect and column effect. Okay. So here are the calculation. Again, you have to have these 2 separate columns. So I'm trying to build a column with the data frame function. So the number that we have here is 12 number. I put 12 number into the vector X. And then we have, and as far as the cars, the type of cars will go, it'll be 1111, and then 2222, and then 3333. So that's how I end, and the number of cars is that column, and number type of gas is 1234, 1234, and 1234. So you build the data frame, you get first column being the X value, second column being the type of car value, and the last column being the gasoline. So you end up having a 3-column data set. With that 3-column data set, you can run an ANOVA procedure. Any question? Okay, so in the summary, this is the result. When we run the summary, I run it on my computer, and you can see the same F value, 18 and 15, and those are probably the p-value. And you can see both of them is very strong significance. Any question? The below is explaining those marks. Whenever there's 2 star, it representing significant at 1% level. All right, so one more thing, when there are 2-way ANOVA, there's additional factor. Instead of factor A and factor B, you have 2 factor 2-way ANOVA. But then what about the interaction? This is explaining that in a 2-way ANOVA problem, one of the things, what about the combined effect? So these 2 factors, they might interact differently from what's expected from the additive property. So sometimes the relation might be surprising, right? So sometimes you find the one that has a lower performance as far compared to the other cars, but when you combine it with one other factor, one particular type of gasoline, but somehow it lasts longer, somehow it performs better. And then that you cannot see unless you combine those effects. So here it says for 9.4-1, gasoline 3 seems to be the best. gasoline, and car 1 is the best of cars. You might think that gasoline 3 combined with car 1 will be the best performing, right? If you single factor, if you only consider gasoline, then gasoline 3 is best. If you only compare the cars, car 1 is best. But when you mix them together, so there may be a interaction. When combine both the factors, the one that perform the best may not be gasoline 3 car 1, maybe somehow one of the cars, one of the combinations. So that's kind of the reason we want to study the interaction between different factors. That's the joint performance. So this situation is called the interaction effect, and here, let's see how do we do it. So basically, you will have. Okay, so study the interaction effect. We have to label them a little bit in more detail. So assume X, I, J, K represents I is which factor A is chosen, and J represents which factor of B factor value we're choosing, and then K representing 1, 2. Suppose you have in box IJ, you have K example, right? So for example, car 3, gasoline 1, you may have 3 cars in there. And then the K will be 3. So basically, for example, let's see what we have here. All right, in this example, we have only one example in each box, but you may have, what if you have 3 here, 3 here, and 3 here, 3 here? So if you want to study interaction, you have to have more examples in each box. Right? In this example, there's only one, so you can hardly tell. Normally, the one the best should be the one combined with the best car, combined with the best gasoline. But then in reality, we should have more examples in each scenario. Other than this case situation, you have 1 car, 1 gasoline in each scenario. Would have more than 1. All right, so that's why we add a C. So in this case, the total number of data point is A times B times C. A represent number of rows, B represent number of columns, C represent in that row, that column, how many data points we have. Oh, so we're time. As far as this interaction, let's leave it for Wednesday. For Wednesday, where we are, as far as quiz. Okay, so this time let's do 8.3, 8.4. I'll see you Wednesday. Thank you.